Today we're going to look at the overfitting problem in classification. To illustrate this, we're going to use logistic regression, which is the classifier, the binary classifier we saw last week. So I'm going to start by explaining some ideas of how we can score the performance of classifiers in binary classification. So different ways of looking at how to measure this performance. And then I'm going to expand a bit on that approach we saw last week, which was to use a training set and a validation set in order to optimize some metaparameter or the model we are going to select. And we're going to extend that to cross-validation, which is a more sophisticated approach, a bit more complex, but one that allows us to mitigate a bit the stochastic effects of using a sample of points to do these estimates. And then we're going to see how we can do model selection and regularization in logistic regression using cross-validation. So first let's start with the problem of evaluating the performance of a binary classifier. So for regression, we used the sum of the squares of the differences between our predictions and the labels as a measure of the error. And this was useful both for minimizing this function in order to optimize the parameters under that assumption of a normally distributed error on the variable that we're trying to predict, and also to evaluate the result. With logistic regression, we are minimizing this cross-entropy function, which is this sum of the target labels. These target labels can be 0 or 1, and multiplied by the logarithm of the probability that we are estimating that an example belongs to class 1. And this function here, the logistic function, is the one that gives us that probability estimate. So one natural score to use with logistic regression to evaluate the performance would be the actual loss function. So the smaller it is, the better the performance of our One problem is that this cross-correlation, this loss function for logistic regression is not very intuitive to interpret. And when we are dealing with binary classifiers, we may want something that tells us a bit more clearly whether or not the classification is correct or if it's making a mistake. So one thing that we can do is, instead of using this cross-entropy function or the logistic loss, is to use something that is analogous to this quadratic error, but instead of measuring a distance between the point and the discriminant, we are measuring the discrepancy between the predicted probability of belonging to some class and the actual belonging or not to that class. So a point either belongs to the class, so if it belongs to the class, it belongs to that class with the probability of 1, because we are sure it belongs to that class, or it does not, and then in that case the probability is 0. So this t here is the target value. It's 1 or 0 depending on the class the point belongs to. And this g is what our model, our hypothesis, trained hypothesis, or each particular hypothesis that we are scanning is predicting to be the probability of this point belonging to class 1. So the Breyer score simply applies this idea of a quadratic error to measuring the difference between the probability we are predicting for class 1 of a point and whether or not that point belongs to class 1. Note that this is not the same as using a quadratic error as the distance to the discriminant plane, so that hyperplane that separates the two classes. It's measuring how much the error is in the predictions of the probabilities of our hypothesis. So a visualization of this would be, for this data set, we could consider that these points belong to class 0, so they are here at the plane of 0. These points belong to class 1, they are here, and one hypothesis would give us this sigmoid function that predicts the probabilities, and we would measure the difference between the predicted probability at each point and the actual class label of the point. And this would give us an idea of how far away from the actual probabilities our hypothesis is. Another useful way of looking at the results of a binary classifier is this idea of the confusion matrix, which tells us when, in which cases does our hypothesis make the correct prediction, or what kind of mistakes it makes. So this table has as columns the actual class of each example. And here in different rows are the predictions of our model. So if our hypothesis is predicting to be class 1 an example that actually is class 1, then this is a true positive. The true is because it's making the correct prediction, and it's the positive because it's class 1. The true negative would be a case of an example from class 0 that our hypothesis predicts to be class 0. So it's a true prediction, and it's a negative example because it belongs to class 0. So in a confusion matrix, in general, even if you're not dealing with binary classifiers, the diagonal represents those predictions that are correct. When we are dealing only with two classes, then this is only a 2 by 2 matrix, and we have in these two cells the correct predictions. These ones outside the diagonal are the confusions, the things that our hypothesis is predicting incorrectly. So if the point belongs to class 0 and our hypothesis is saying it belongs to class 1, then our hypothesis is saying it's a positive point, but it's false. So this is a false positive. It's a point that should be negative. It should be predicted as negative because the point belongs to class 0, but our hypothesis is falsely labeling it as a positive. And this is the inverse problem, which is a point of class 1, which is should be positive, but our hypothesis is saying it's negative. So it's a false negative. Now, with these four different possibilities, we can think of different ways of measuring the performance of our binary classifiers. One very used measurement is accuracy, which is simply the fraction of correct predictions. So you can say, you can add the true positives, which are the positives ones that were correctly predicted, and the true negatives, which are the negatives correctly predicted. So these are all the correct predictions, and divide by the total number of examples in the set. So this gives us the fraction of correct predictions, and it's the accuracy of the classifier. And then we have these two different measurements of two different things. One is prediction, which is the true positives among those that our model is saying are positives. So the true positives and the false positives. If we go back here, these are all the examples our hypothesis is telling us they belong to class 1. And the precision measures the fraction of those that actually belong to class 1 among those that our hypothesis is saying belongs to class 1. So for example, if our hypothesis tells us that 10 examples belong to class 1 and 9 of them are true positives but 1 was a mistake, then we have 90% precision. This means that basically how reliable it is that those examples our hypothesis tells us are positive, how reliable that information is, how we can then conclude that they really are positive. Recall is a different concept here. It's the fraction of true positives among all those that should have been classified as positive. So the true positives and the false negatives. So basically recall is the fraction of those correctly identified as positives, divided by the number of points in class 1. So the number of points in this cell and this cell here. And this basically measures the ability of our hypothesis to identify positive examples among all the positive examples in the data set. So the greater the recall, the greater the number of examples our hypothesis is retrieving from the positive class. We can combine these two because usually precision and recall, there can be a trade-off here. We'll see this a bit in a bit more detail, but basically if our hypothesis is telling us a lot of examples are in the positive class, It may be making a lot of mistakes, but it's dragging all the examples in the positive class, or nearly all of them, into that set where the hypothesis say this is positive. So it may have a large recall, but then a very low precision because it includes lots of false positives there. Or it may happen the other way. It may be, have a very high precision, but then leave out a lot of positive examples that it should be classifying as positive. So we can combine these two. For example, the F1 score is the harmonic mean of the two, precision and recall. And we can use this combination as balancing out these two opposing tendencies. But let's see this in a bit more detail when we consider the possibility of changing the threshold. So remember that in logistic regression, we are using that sigmoid function to predict the probabilities of a point belonging to class 1. So let us imagine that this is the data set. This is a mapping of the sigmoid function that is low here, then it starts to rise, and then it's high on this side. So over here, we assign a probability close to 1, and at this line, the probability of being the red point, the positive point, is 0.9. Here is 0.5, so this is where we usually draw the line separating the two classes, when the probability of belonging to one is the same as belonging to the other. And then here, the probability of being a red point is only 0.1, and so on. But more generally, we usually separate the two at 0.5, but more generally, we could separate at any different probability. So we can imagine what that happens, what that will result when we look at true positives and false positives. So suppose that we set the threshold at 0. Everything that is 0 or more, our hypothesis classifies in class 1. In that case, we will have all the true positives, because we would classify everything as red, and all of these red points would be correctly classified. But we would also have a large number of false positives, because all the blue points would be classified as positives too. So suppose we drew the line here and said everything on this side is red. As we increase the threshold, we start discarding blue points from class 1, so we start losing these false positives. But eventually, if we keep increasing the threshold, we start losing red points too, as we move the line to this part. So if we increase the threshold where we separate the positive and negative class, we start losing false positives, which is good, but eventually we start losing true positives too. And if we set the threshold at 1, so on this side, everything that is below 1, we consider it to be blue point, to be class 0. In that case, we will not have any false positive because everything is considered to be class 0, but we also won't have true positives because we discard all the red points too. So intuitively, we can imagine that as we scan through the threshold, we have these two lines where the false positives start to decrease and then the true positives start to decrease too. And the separation between these two should give us an indication of how good our classifier is. If we cannot separate the two, then the classifier is useless. If we can separate them, we can find some ideal place here where we minimize the number of mistakes. So this is, if we transform a bit this plot, so this plot is done as a function of the threshold, and I'm drawing the two lines, the false positives and the true positives and the false positives, but I could draw one as a function of the other. So this is the rate of false positives and the rate of true positives. Ideally, I should have a point over here, which would mean that I would have 0% false positives and 100% true positives. That would be the ideal classifier. It would do something like this. A classifier that goes here on the diagonal, it would be useless because as we increase the number of true positives, we would also increase the number of false positives equally and would be unable to distinguish between the two. And this curve here, when you draw the true positives as a function of the false positives, is called the receiver operating characteristic curve. Now, this name is very strange because it doesn't seem related to anything that we are looking at here. But this is an historical name because this curve was used first during World War II to calibrate radar detection. So the operator of the receiver was the person that was operating the radar receiver and trying to distinguish between enemy airplanes and things like storm clouds or flocks of birds or things like that that could interfere with radar detection. And depending on how sensitive the receiver was, the person would be able to detect enemy airplanes more easily, so it would have a higher rate of true positives, but then other things would be more confusing and they could make mistakes like identifying storm clouds or things like that as enemy airplanes, so the number of false positives would also increase. And since this curve was characteristic for each operator, for each person, this would be the characteristic curve for each different person and would determine how best to calibrate the radar receiver. So that's why we have this very strange name, but in machine learning we just call it the ROC curve and not worry too much about the name and the history. And the idea here is that we can use the area under the curve also as a measure to evaluate the performance of a binary classifier. If our classifier has a ROC curve that's something like this on the diagonal, then it's really useless. We cannot we are making as many mistakes as we are finding the correct examples. If it's all the way up here, then it's a perfect classifier, because with zero false positive rates, we can have 100% true positive rate, and that would be ideal. So the more this curve approaches the corner there, the better the classifier would be. So for scoring binary classifiers, we can in the case of logistic regression, we can use the loss function, we can use the Breyer score, any classifier that tells us the probability of belonging to class 1. We can easily compute the Breyer score for that classifier, because that's just the mean of the quadratic residual of the predictions relative to the class the examples belong to. And then we have these measures: precision, recall, accuracy. We can plot the confusion matrix and so on. For classifiers in scikit-learn, one very easy measure to use is accuracy, because in scikit-learn all these classifiers have this score method. So the general procedure for using these classifiers is you create an object of the classifier by calling the class. So you generate an object. Usually you can put the parameters here if you don't want to use the default. This will depend on different classifiers. Then you fit the internal parameters of the classifier. That is, you train the model so that you get a specific hypothesis by giving the features, so the X values, and the target labels for the classes, the epsilon values. After the classifier is trained, we have a specific hypothesis. Then we can use the score method of this object to tell us how what was the percentage of correctly classified examples in some data set. For example, here we could use the training set in this case, and then the test set here, and measure the score in the test set. The score corresponds to accuracy because it's the fraction of correctly classified examples. If instead of accuracy you want the fraction of errors or the fraction of incorrectly classified examples, you can just do 1 minus the score, and this gives us the error, which is usually what I represent in those plots where down is good and up is bad, basically. Okay, so now let's see, using these scores and extending a bit the idea of training, validation, and test, we'll see this approach of cross-validation. So last week we saw that we are minimizing the training error to generate or to choose an hypothesis from the hypothesis class. This makes the training error extremely biased, because we were running through lots of different hypotheses until we picked this one, because it minimized the training error. So the training error is a very biased estimate of the true error, and it will be underestimating the true error of our hypothesis. So in order to properly evaluate different hypotheses and compare them in order, for example, to select the best model to use, we set aside a different set, the validation set, and measure the error on that set. So this is the validation error, which for each particular instance is unbiased when we measure it, but when we measure it over different instances and choose the smallest one deliberately, then we make that estimate biased because we threw the dice several times and chose the smallest one. This, by the way, can also happen if you just press F5 and run your script several times until you get a good result. If you do that, you are biasing everything, and so your estimates will now be underestimating the true error of your hypothesis. So this is the general idea of what we do with the validation error. We try different things and choose the one with the smallest error, and that makes it biased. So we keep the test error to the end. We don't decide anything based on that test set, and use the test error to obtain an unbiased estimate of the true error. So this was the approach we saw last week. However, there is one problem here. We are selecting, for example, the model based only on one estimate of the validation error. And as we saw, this will depend a lot on which points are assigned to the training set and which points are on the validation set. So depending on that distribution, we can get different results when we train with one set and validate with the other, even when using the same model. So to try to mitigate this effect a bit, we can use cross-validations where we're going to average over different hypotheses of the same model, and then use that average as an indicator of how good the model is on average when trained with this kind of data for solving this particular problem. So we're going to split the data into two sets, the training set and the test set. Usually, most of the examples will be in the training set, unless you have a huge data set, but usually most of them will be in the training set, and we set aside the test set just to use at the end to get an unbiased estimate of the true error. And now we're going to use the training set to try to find the best model, for example. We're going to split the training set into k folds. So this can be 5 folds or 10 folds. Usually it's around that number. And we're going to train the model using k minus 1 of these folds. For example, if we split into 10 folds, we're going to train using 9 of them and then measure the validation error on the fold that is left out. And then we're going to leave out a different fold and repeat the whole process. So if k equals 10, we do this 10 times. If k equals 5, we do this 5 times. And each time we are training with k minus 1 of the folds and test in validating or measuring the validation error on the points that are left out. So to try to illustrate this here, suppose that we have this data set, and this is our training set here. So all these points, red and blue, are ordered like this. I'm going to split this into 5 folds and use this set of points here, the ones that are larger, for validation and the rest for training. So I train with all these smaller points, I get this curve, and then I measure the error on the validation set, and it's 0. It happened to be the case that all these points fell on the right side of the curve. But now I'm going to do this again. I'm going to select a different subset of points for validation, and I'm going to train with the rest. So I'm going to train with these and all of these here and validate with this fold here. And then I'm going to do this again and again. So you see each time the curve is slightly different because the points I'm using for training are different. And the validation error is also different because it depends on where the validation points are lying. And I'm always using the same model in this case, but I'm getting different hypotheses because I have different training sets. And now I average everything. So my estimate for what the true error of the model would be on average on this kind of data would be the average of these validation errors. So this is what I estimate the error of the model would be on average on this kind of data. Note that this average is not the validation error of any specific hypothesis because I'm averaging over several hypotheses. But it gives me a better idea of what on average would be the validation error for this model when trained with this sort of data. So with training and validation, what we saw last week, we are using the estimate of the true error on one single hypothesis and then using that to select, for example, different models. And this is not very good because that hypothesis may happen to be that way because of the training set, because of the way we split things, and it's just one sample. So with cross-validation, we average over different hypotheses taken from the same model by using different combinations of points in the training set and the validation set, and we average those validation errors. So this gives us a better estimate of the true error for that on average hypothesis generated from that model would give us. But it's not the actual error of any specific hypothesis that we are dealing with. Okay, so after we do this, we select the model. How can we get the final hypothesis? Now we can use the final, the whole training set and train the model with all our data. So there is a special case with k-fold cross-validation when you have as many folds as you have points. This sometimes happens when you have very few data points. For example, you only have 20 points and you don't want to waste anything on validation, or as few as possible. So you can do 20-fold cross-validation, and at each fold you are training with 19 points and measuring the error only on one point that was left out. And then you do that again and again and again, leaving out different points. So this is leave one out cross-validation. But this, however, is a very extreme example when you have very few data points. One problem that occurs both in validation, cross-validation and testing, but it's especially the case in cross-validation when, because you have to split into several folds, is the possibility of having a class imbalance. So suppose that you have one fold, in this case, imagine that one of these folds only had blue points and another one only had red points and things like that. This would probably make the results a bit weirder and make the error oscillate too much, and we can try to avoid that. So usually what we do is to use stratified sampling, which is a way of randomly sampling the points into the different folds, but doing it in such a way that the proportion of points from different classes remains the same. So we are taking at random, but keeping as much as possible the same proportion for each class. So let's see an example here in logistic regression. We're going to use this data. This is an artificial data set. It doesn't mean anything, but it's good to represent these curves and to see how we can try to classify these points. So we're going to start by loading the data, shuffling everything, and standardizing. This is the general approach. I'm going to talk a bit more detail about this further on, but in general, you should shuffle the data because you don't know what the order of the data points is in the training set. So for example, suppose that you are dealing with medical data and the data set that you had was sorted by age. In that case, there would be a strong correlation between the position of each point on the table and some kinds of medical problems. And you could get very incorrect results simply because you were sorting everything by age and splitting apart for example, the eldest people for the test set or something like that, and would be very confusing. So in general, it's best to remove all these correlations with the position of the points on the data set by shuffling. And you can use this from scikit-learn utils. You have this shuffle method that returns a copy of the array you provide shuffled at random. Note that this is shuffled along the first dimension. So if you give as an argument a two-dimensional matrix, it will shuffle the rows but not shuffle the columns, which is good because we don't want to shuffle the columns since those are the different features. Also, one important thing, you also have a shuffle method on NumPy, a NumPy random, that works exactly the same, except that it shuffles in place. So the shuffle from scikit-learn utils returns a copy, and you need to store it in some matrix. The shuffle from NumPy random does shuffling in place. You can use either of them, but be aware of this difference in what they do, because you may be ruining the original data or not getting a copy or something like that, and then you have a bug in the program if you confuse the two. So what we can do here is we shuffle the data. We can separate the Y values and the features. So in this case, the class labels are in the first column here, and the other columns are the X values, the features, which are the coordinates for each point. So X1, X2 here. We want to separate them because we don't want to standardize the class labels. The class labels are just 0 and 1. It doesn't make sense to rescale anything there. And we're going to rescale the features so that they have a mean of 0 and a standard deviation of 1. So that's what we're doing here. We are standardizing the features. In a real application, always remember to retain these vectors, because then you need to do the computation back again when you introduce new points to predict. But we can do this in one go with our data set and then split into training, validation, and testing. Actually, if we are very rigorous about this, we should use rescaling only on the training set and use the same parameters for the test set. However, we are not going to worry too much about this, and I'm going to explain why in a few lectures, because statistically that ends up not making any difference, so we don't need to waste time with those details. So just standardize everything. That is the general approach. It's the simplest approach. And now what we're going to do is to use logistic regression to try to find the best frontier here. Now, one problem is that logistic regression is a linear classifier. So if we just put in these features, we are going to have a straight line crossing here, and we cannot distinguish between the two classes. However, we saw this idea several times now, that we can transform our data into a higher dimensional space using nonlinear transformations, and now we are bending the surface of our data in this higher dimensional space, where cutting with a straight hyperplane can actually, in some cases, distinguish between these two classes, because we have bent the data enough for that. So to do that, we're going to consider different models. We're going to apply logistic regression with only two features, the X1 and X2, which are the original features here, or with three features by adding the product of X1 and X2, or four features by adding also the square of X1, and so on and so on. So we can do this expansion up to 16 features, where we create a new expanded matrix that has the same number of rows as our data and has additional 14 columns for the features. And now we're going to copy the first two columns into the first two columns of the expanded data. So these are the original features that we have from our data, and then we keep adding to different columns different expansions. So the product, the square, the cube, the square multiplied by the other one, and so on. So we can write this function to expand everything to 16 features, and then we can select which model just by choosing the first two columns, or the first three columns, the first four, and so on, and we can explore different models. Just one side note, this is not something that you will do in practice when you're dealing with real problems. Because if you need to do classification on a data set that is not linearly separable, so something like this, then you're probably not going to use logistic regression. You're going to use something like support vector machine or something like that, that does this thing implicitly and doesn't cost us anything. But the purpose of doing this by hand at this stage is just to help you understand what is happening here, so that this thing does not appear to be some kind of witchcraft when the classifier manages to separate the data. Okay, so we are going to create this new matrix by expanding the features of our original data, and we're going to split into a training and test set. We did this last week by hand just to show you how we split at random and so on, but we're not going to do that to have that extra work anymore. Now that you already know what this split is and what the algorithm is doing, we're going to just import from this model selection module the train test split function. So this function receives a matrix with the features, the vector with the class labels, and the fraction of points we want to retain on the test set. So in this case, I'm going to put 1/3 for testing, 2/3 for training. You can also specify how you want to stratify. So stratification means that the split will be done at random, but in a way that keeps the same proportions of something that you specify here. So in this case, we're going to specify the class labels, which means that if we have, for example, 50% class 0, 50% class 1, then our training set is guaranteed to have 50% each, and the test set will have 50% each. So this is very practical to keep the class balanced in the training and the test set. And now we're going to do k-fold cross-validation. So we're going to do cross-validation to select the best model here. And to do that, we're going to use this k-fold class, which is very practical for solving this problem. So basically, you create an object that is iterable, that you can iterate through in a loop, specifying how many splits you want to create. And then when you call this object to split some data that you have, it will give you the indexes that you need for each fold. So for example, in this case, we want to split into 4 folds. And now for each iteration, this will give us a tuple with the indexes for the training set and the indexes for the validation set of this vector here. Note that the only thing this kf split is looking at in this vector is actually the size, because it's going to give us the index for these values here. And this is what's happening here. So in the first iteration, it sets aside the first 3 points for testing and the others for training. And then it sets aside points of index 3, 4, and 5. So points on the 4th, 5th, and 6th position. Remember that Python starts counting at 0 for testing, and the others for training, and so on and so on. So this makes it very easy to figure out on each pass which points we're going to use for training and which points we're going to use for validation. So we can use this k-fold, or you can use stratified k-fold. It does the same thing, but you can you give it 2 arguments. One is just for the object to know how many data points you have, so it actually ignores the values there. But the second one is the one it's going to use for stratification. And what this will do is to try to split into different folds in a way that preserves as much as possible the balance between the values. So let's look at this example. We have here in the first fold, the first iteration, the test points are the first 3 points here, 1, 1, 0. Okay. So these are the first 3 indexes of the array. And then on the second fold, it's going to use all these for training, and for test, the other ones here. So you see, in both these cases, there are 2 1s and 1 0, 2 1s and 1 0. It's keeping the same proportion. But now, if it were to use these 3, it will have 2 zeros and only 1 1. So in this case, it's going to change, and the 9th one will come here, and that one of index 8 is left to the end. So it's going to put one of these ones into the fold number 3, and this 0 is going to shift it to fold number 4. This way, it keeps the balance of zeros and ones in all these folds. So in general, stratified k-fold is probably the safest bet. It keeps your data balanced across the different folds. If you have lots and lots of data points, then this is unlikely to make any difference, because in that case, it's statistically unlikely that you'll have very different balancing of the different classes in different folds. But if you have small data sets, then it's important to try to keep this balance. Okay, so now we're going to compute the train and the validation errors by using the Breyer score. You can use the accuracy if you want. The Breyer score has just a small advantage that it's a continuous value. So if you have many data points, accuracy is almost continuous because changing the classification of 1 point makes a very small change in the fraction of correctly classified points. But if you have few data points, for example, 50 data points, then sometimes you can actually see the little steps on the plot because changing 1 point will already change the accuracy by a significant step. So in this case, 2%. If you use Breyer score, this is a bit prettier because it's now continuous. You are comparing the probabilities estimated by the logistic regression with the target values, and it's a continuous function there. So what we're going to do here is we create this auxiliary function that receives the matrix with the features. This is the expanded matrix with all these extra features that we created here. And it receives the class labels, the number of features that we want to use, and which indexes or which rows we're going to use for training and which rows we're going to use for validation. So basically, we create a logistic regression object here with this value for regularization. I'm going to talk about that in a few minutes, but this is basically a very high C means you have a very low regularization. It's almost no regularization here. And you can add also this tolerance to specify when the optimization ends. And you can see more options in the documentation. So take a look at logistic regression in the scikit-learn documentation to see what other options you have. But basically, this line just creates the logistic regression classifier object. And then we're going to train it by calling the fit method, using as features only the first columns of our matrix. So if fits here is 5, we'll be using the first 5 columns of the matrix. If it's 2, then it's the first 2 columns, which is just the original data. And we're going to use those rows that correspond to the training indexes. So we're going to fit logistic regression using only the folds reserved for training. And we're going to fit it so that it matches the same examples in the class labels. So we're also using the indexes for training here. And now we're going to predict the probability for all the points, all the points in the training set. And we're going to separate this into the error for the points that we have assigned to the folds for training in this particular instance, and those that are assigned for validation. So basically, we are computing these errors for all the points in our data set, all the differences between what the class label should be and what the probability was predicted by this hypothesis. We square all these values, and then we return the average of that for the points used for training and the average for that on the points used for validation. So basically, this auxiliary function receives the data and how many features we want. It fits the logistic regression model, gets a specific hypothesis, and then evaluates that hypothesis on the training data and on the validation data so that we have an idea of what the error is. And what the error is measured here is the Breyer score. So now we can do cross-validation. We can choose, for example, 10 folds. We create a stratified k-fold object for splitting into 10 folds. And now for each number of features, we are going to start with 2 and then 3, 4 and so on. We're going to iterate through all the folds. So we're going to split our training data into these 10 folds and compute the training error and the validation error after training with the training folds and measuring on the validation fold. So this is 10 times for each number of features that we want. And we repeat this for all the different number of features. And then we can print out the average training error and the average validation error after each cross-validation cycle here. So this is an example of the results. If we use 2 features, here are the different hypotheses that we are seeing. So we have 10-fold cross-validation. This means that we are creating 10 different hypotheses by training on 10 different subsets of our training data using those combinations of folds. So these are the lines here. And this is the cross-validation error that we obtained. So the average error on the validation set for these 10 lines using only these two features. Note that when we only use these two features, this is a linear classifier, logistic regression, so the frontier here is always a straight line. If we add the product of the two, so these three features would be these three here, the original two plus the product. So this is now the second model we are trying. We start getting some curved lines here, because now we bent our data into three-dimensional space. We cut with a straight plane there, but when we project back, we have these curves. And now we can do this with 4 features, 5 features, 6 features, and so on, and we start getting different results. Also note that we're going to look at this into more detail in a few weeks, but note that as we increase the power of the model, we also increase the divergence, this variance between the different hypotheses that we get as we change the different data sets, because now the model is more capable of adjusting to the points. And we can increase, for example, here 12 features, we see that it starts getting some strange results. And we also note that the cross-validation error is increasing. So basically, when we plot the training and validation error using cross-validation, so this is the average training error for each number of features, and this is the average validation error, we can see that we have this underfitting region here, where the training error is very high because our model is too stiff and cannot curve enough to properly separate the classes. But then it starts getting too flexible and starts increasing the error again. So this should be around 9, using the first 9 features should be the best in this case, at least between the ones that we tried. So this would be our best model. Okay, so by cross-validation we found the best model, but note that we don't have a specific hypothesis yet, because even if we go back to 9 features here, we have 10 different hypotheses, each one trained with one different subset of the training set that we obtained by cross-validation. So now what we need to do is we take the whole training set and train this particular model that we chose, the one with 9 features, on the whole training set. We are no longer using those folds, no longer partitioning, using all the training data. And then we measure the test error to get this unbiased estimate of the error. So this would be the unbiased estimate of the true error of this particular hypothesis that we got after selecting the best model and training with a complete training set. So remember this part: after doing cross-validation and selecting your model, train this model with the whole training set, and this would be your final hypothesis. Now you just measure the test error to get an unbiased estimate of the true error. So basically the recipe is like this. You do all your pre-processing, you remember to shuffle the data. You never know how the data is sorted, so it's best to shuffle everything. If it's sorted by class, then it will be a nightmare, because you'll have all the points of one class first and all the points of another class second. It may be sorted by some feature, so we need to shuffle to remove those correlations. You can rescale, normalization or standardization. Usually standardization works best. It deals better with outliers. If you have something that you know must fall within some specific range, then normalization is a good approach too. Reserve a test set. This one will be used just to estimate the true error. And now you partition the training set into a number of folds, for example 5 folds or 10 folds. In both cases, if you don't have a large data set, you should consider using stratified splitting, because it guarantees that you'll have a better balance of your classes. Then you select the best model with cross-validation, and after you select the best model, you train this model with the complete training set. And this will give you the final hypothesis that you produce, for which then you can estimate the true error using the test set. Note that even though the cross-validation error is an unbiased estimate of the true error, and if you're not doing any model selection or choosing anything. You can actually use cross-validation instead of a test set, just to get an estimate of the true error. But the problem is that if you are using cross-validation to select the best model, you are picking the smallest of a set of values. And this choice of choosing the smallest value will make the value biased. So this is why you need the test set if you are choosing the best model. Okay, so this is dealing with overfitting using model selection. Now let's look at a different approach to dealing with overfitting, which is using regularization. So remember, we saw the last time with regression, regularization is the general approach of changing the way the model is trained in order to minimize the effects of overfitting. So with logistic regression, we can use this L2 norm also, like we used in ridge regression, which is penalizing the weights of our model or the parameters that we are fitting. In scikit-learn, you have this C parameter that we saw previously. So this C parameter here that we included here is the weight given to regularization. And actually, this seems a bit strange, but it will make more intuitive sense when we look at support vector machines. But in scikit-learn, you use a C parameter that is high when you want very low regularization. So actually, instead of using this lambda here for the general expression of the L2 norm, you use 1 over C for the weight of the regularization parameter. So if C is 10 raised to the power of 12, this is 1 over 10 raised to the power of 12, so this is very close to 0. Now, in ridge regression, it's intuitive why this penalty works. Imagine that we are adjusting a degree 2 polynomial, for example. We have the quadratic error that we are minimizing, but then we also add this penalty as a function of the size of the magnitude of these coefficients. So if our polynomial needs to curve too much, these coefficients need to get larger and the penalty increases. So, and this penalty will tend to make the coefficients closer to 0, and this will make the polynomial curve stiffer and not able to curve so much. In logistic regression, it's strange how this works, because we are penalizing the weights of the vector that is perpendicular to the discriminant, so this vector here, and it's not clear what use that will be, because we are separating the classes in this plane here, and this vector is only indicating where the plane is and which side is class 1. So having this vector larger or smaller should not make a difference to how we are classifying. And so we need to see what is happening behind the computations that when we are fitting the model, to understand how this works in regularization. So this is the logistic function. This this plane that we have here is the one we chose at 0.5 probability. So we have the logistic function that estimates the probability of belonging to class 1, and we draw this hyperplane at the midpoint here. If the vector can be arbitrarily large, so this inner product here can be arbitrarily large, then this step can be very steep. It goes all the way close to 0 and then suddenly jumps and is 1 here. If we force this vector to be smaller, then we are actually making the slope lower, because now it takes longer for the function to rise from 0 to 1 if these values are lower. And this is why this has a regularizing effect. Suppose that we have these data here, these data points. We have a blue point here very close to the red one, and if we don't use regularization, logistic regression can draw the frontier here, because it's 0 probability of being red, and then it suddenly jumps to 1, and now it's probability 1 of being red, and it can separate the data here. But this is clearly overfitting, because this is an outlier, and it would be much safer to place the frontier somewhere around here, where the two different data sets are further apart, so have a larger margin. And we can do this if we force the slope to be lower. Because if we force the slope to be lower, the frontier cannot be placed here because it takes a while to get all the way to 1, and it will have a very large error for all these points here. It's much better to just sacrifice this point and move the discriminant a bit down so that we can have a smoother slope here without making too many mistakes and not penalizing too much the error. So this is why penalizing the size of the parameters will work as regularization in logistic regression, because it forces the slope of the logistic function to be lower, so to increase more slowly, and this makes it forces the discriminant to move away from where the larger clouds of points are. So this can reduce overfitting. Let's try this with our example. We're going to use 15 features in this case, which we saw was had lots of overfitting, so lots of different hypotheses here, a higher validation error. But now we're going to use regularization, and we're going to optimize the regularization parameter in the same way. We're going to loop through different values of regularization. Actually, I'm showing the logarithm of C, that C parameter. The higher the C is, the lower the regularization effect, so the weight of the regularization. And we can see that as we decrease regularization, the training error decreases, because as we decrease regularization, the easier it is to adjust to the data. But eventually the validation, the cross-validation error starts to increase a bit. And we can see the minimum to be here at around C at 10 raised to the power of 5. This is a logarithmic scale. And so we can use that. We can use this 15 feature model, but with a small amount of regularization. Remember that this is 1 over 10 raised to the power of 5. Just this tiny bit of regularization, it's enough to stabilize everything there. And now we have a very good discrimination between the two classes. So just one small reminder, this thing that we are doing here by manually expanding the data and then using this matrix with different number of columns and so on, this is just so, to help understand this idea of projecting into a higher space with a nonlinear transformation and then applying the linear classifier into that space. In practice, if you need to do this, you're going to use other types of classifiers and not logistic regression, and we're going to see those later, like support vector machines. But this is a very important idea, because we tend to base everything on linear classifiers, at least these kinds of classifiers, and then do these expansions to go to solve nonlinear problems. Okay, so to sum up for this first block, we saw how to score and evaluate classifiers, the confusion matrix, accuracy, recall, precision, and so on. And we saw cross-validation as an extension of that idea of train, validation, and test. Just remember that when you're doing cross-validation to select models or regularization, hyperparameter, something like that, you are taking the average of different hypotheses as an estimate of what, on average, will be the performance of the model on that kind of data. This means that once you select your hyperparameters or your best model, you need to train with the whole training set in order to get the final hypothesis. And that will be the hypothesis that you test at the end. We also saw this idea of stratified sampling. This is important to prevent unbalancing your classes on your data sets. So I recommend reading section 2.7 of Alpidon, and we'll continue on part 2 in about 10 minutes. So 10 minutes after 5, let's have a short break in the meantime. See you soon.